So NASA just caught something absolutely wild from 3IATLAS today. And honestly, nobody's completely sure what to make of it yet. You know, for weeks now, we've all been watching this thing. And yeah, it's been strange, but at least there was a rhythm to it. At least we could look at the data and say, okay, we're seeing patterns here. We're getting a handle on this. Today's flash just completely shattered that comfortable feeling. It's like the comet looked at us and said, "You thought you understood me. Watch this." Before I dive into what actually went down, I just want to say if you've been following along with me on this journey tracking this interstellar visitor, if you want to catch every single twist and turn as it happens, make sure you're subscribed and like. And honestly, stick around till the end of this one because what we're seeing today might be the clearest indication yet that 3IATLAS is hiding something underneath that we still haven't figured out. So, let me tell you what NASA observed. The thing is, this newest batch of data wasn't supposed to be anything special. It was just routine work, you know, same instruments they've been using, same timing between observations, same careful tracking of 3IATLAS as it continues its journey away from the sun. Just another day of monitoring this interstellar traveler. They're going through the frames. Frame 1 looks normal. Frame 2 also normal. Everything's tracking as expected. And then frame 3 comes up and suddenly the comet gets noticeably brighter. Now, it's not the entire image that's lighting up. It's not some flare from the sun messing with the exposure. This is a tight, compact brightening happening right there in the inner coma of the comet. It's like watching someone flick on a light switch inside this hazy cloud surrounding the nucleus. The flash stuck around just long enough to show up across multiple exposures, so we know it's real. It's not just a single frame glitch. And then just as suddenly as it appeared, the brightness dropped right back down to baseline levels, back to where it was before, like nothing had happened. There's no slow build-up to it. No gradual fade out, just a sharp spike in brightness, and then it's gone. That right there is the first seriously weird part about all this. See, when comets have outbursts, and they do have them, they usually look messy. There's this characteristic look to them. They tend to evolve over hours, blowing dust and gas outward in ways you can literally see, spreading and diffusing between successive frames. It's gradual. It's visible. It makes sense. This flash didn't do any of that. It didn't smear or spread or evolve gradually. It just snapped on and snapped off. So, naturally, the teams did what good scientists always do. They tried to explain it away. They went hunting for every possible reason this could be. An instrumental artifact rather than something real. They checked for cosmic rays hitting the detector because those can create false brightening events. They checked for satellite trails passing through the field of view. They looked at bad pixels. They examined guiding errors. They went through every single thing that could potentially fake a short, sharp burst of light like this. And they came up empty. Nothing matched what they were seeing. The brightening was centered directly on 3IATLAS itself. It moved through the frames exactly matching the comet's own motion across the sky. And critically, the surrounding star field stayed completely stable. Nothing else in the image changed, which means there's really only one conclusion here. The flash came from the object itself. This is real comet activity we're looking at. Now, here's where things get even more bizarre. The teams did something clever. They stacked the images and did what's called difference subtraction. Basically, they took the normal baseline 3IATLAS and subtracted it from flash mode 3IATLAS to see what was actually different, what was producing that extra light. And something really interesting popped out of that analysis. The extra light isn't spread out evenly across the coma like you might expect. Instead, it's concentrated along this narrow axis and it's offset slightly from the main tail direction. Try to picture this. You've got the coma, which is normally this roughly round glow surrounding the nucleus. You've got the tail streaming away from the sun like you'd expect from a comet. And then during this flash event, there's this bright bar cutting across the inner region at a completely different angle from the tail. And here's the kicker. That bar, that concentrated brightening, It lines up almost perfectly with one of the spots they've suspected is an active region on the nucleus. It's been faint in earlier observations, but it's persistent. It keeps showing up in high-contrast images of the comet. So, what did NASA probably just witness here? The theory that's getting the most traction right now is that we just caught a localized high-energy event suddenly firing off. Like a micro-outburst from a single crack or maybe a specific patch on the nucleus surface. But you know what? Calling it a micro-outburst might actually be underselling what happened here. Because when the team sat down and actually measured how much the brightness jumped and more importantly how quickly it happened, the numbers are kind of insane. To produce that kind of dramatic flash in such a short time window, that vent would have had to dump an enormous amount of material in a burst that's measured in minutes, not hours. That's incredibly fast for these kinds of events. And that suggests something important. Pressure. Real significant pressure. Something inside 3IATLAS was building up gas faster than it could slowly leak out through the surface. The pressure kept building until whatever was sealing it in finally failed. Catastrophically. Think about it like this. Imagine there's this ancient pocket of volatile ice deep inside the comet, right? It's been there for billions of years just sitting dormant. And then as the comet swings through our solar system, that ice finally crosses some critical temperature threshold. It starts expanding. The pressure builds. It's pushing against the crust above it harder and harder until that crust just can't take it anymore and cracks. And then whoosh, everything erupts violently into space. That would absolutely explain why the brightening looks like a narrow beam. It would explain the suddenness of it. And it might even explain something else the tracking teams noticed afterward. Because this flash wasn't just a visual spectacle. It had physical consequences. Right after the time window of this event, the orbit calculation teams started picking up on something subtle, but definitely real. A tiny change in the comet's residuals. Let me explain what that means. If you compare where the comet should be based purely on gravitational forces, the sun's pull, the planets, all that versus where it actually is now after including this new data point. There's a slight offset, a tiny discrepancy. It's incredibly small. Not something you'd ever feel if you were standing on Earth or anything like that, but it's big enough that the precision orbital software flags it and says, hey, something pushed this object. Something gave it a little nudge. And that's exactly precisely what you would expect if a one-sided high-energy jet just briefly fired from the nucleus for a few minutes there. 3IATLAS essentially lit a thruster on one side and gave itself a tiny push. But here's the problem with all this, and this is what's got people really scratching their heads. When you actually run the numbers on this, that brief thruster turns out to be more efficient than anyone expected it could be. Based on the amount of brightening they observed, based on standard models of how much gas and dust that would represent, that material shouldn't have been able to produce quite that much push on the comet. The math doesn't quite add up. So, you're left with two possibilities, and neither one is particularly easy to swallow. Either the material was being ejected at higher speeds than our standard models allow for, which means we need to fundamentally rethink how gas can accelerate through these fractures and vents, or we're significantly underestimating how much actual mass came out during that flash. Which means we need to go back and revisit everything we think we know about the comet's internal structure and stability. Because if it's shedding chunks at this rate, that raises serious questions. And here's the thing you have to remember about all this. This isn't some local comet. This isn't something that formed in our Oort cloud and has been orbiting our sun for billions of years. This thing has been drifting through interstellar space between the stars for billions of years. That crust is probably significantly harder than what we're used to. The internal layers are probably structured in stranger ways. Cosmic radiation has had literally eons to bombard the outer shell to rework it chemically and physically into something we've never actually sampled before in our laboratories. So when an event fails on 3IATLAS, when pressure breaks through and material erupts, it might not behave anything like the comet outbursts we've observed from our homegrown solar system objects. The physics might be subtly different in ways we're only starting to appreciate. That's exactly why this flash matters so much. This isn't just, oh, cool. The comet got brighter for a bit. Neat observation. No, this is a direct glimpse into the fundamental way an interstellar comet stores energy and releases it. It's a real-time test happening right in front of our telescopes of how this thing is actually built beneath the surface. What's it made of? How is it structured? How does it respond to thermal stress? And this flash adds to a pattern we've been seeing, which is honestly starting to get a little concerning. First, we saw jets coming off this comet going in directions they really shouldn't be going based on solar heating models. Then, we saw the coma changing its shape faster than the computer models were comfortable with. Then, we started detecting these non-gravitational forces, these tiny pushes on the comet's orbit, and watching them drift around as the activity pattern shifted across the surface. And now we've caught this discrete, measurable flash like a single heartbeat. And that flash actually produced enough force to measurably nudge the entire comet. So naturally, the question becomes, what happens next? If this was a one-time event, a single occurrence, then it's an incredibly valuable clue about what's going on inside this object. We can study it, model it, learn from it. But if it repeats from the same region, if we start seeing flashes coming from that same active area again and again, then it stops being just a clue and becomes a pattern, a rhythm. And patterns tell us even more about the underlying physics. And if new flashes start showing up from completely different locations scattered across the nucleus, from regions that haven't been active before, then we might be watching 3IATLAS enter an entirely new phase of its existence. A phase where its crust, this ancient radiation-hardened shell, is failing in stages as the comet races back out of the solar system. Multiple weak points giving way one after another. There's also a more dramatic possibility that nobody really wants to say out loud yet, but I'm going to mention it because it's real. A sequence of flashes like this happening with increasing frequency can sometimes be the warning sign that comes before fragmentation. If there's enough internal stress building up, if you get enough rapid venting happening from multiple locations, the comet doesn't just keep flashing. At some point, it cracks, it breaks apart. We've seen this happen with other comets. The structural integrity just fails and the nucleus splits into pieces. Right now, all NASA is officially saying in their reports is that they observed a transient brightening event, a flash that appears to be intrinsic to the comet itself. Very careful, very measured language. But unofficially, everyone who works on this project is on watch now. Eyes are glued to the data feeds because if another flash hits, if the light curve starts showing repeating spikes at regular or irregular intervals, or if the inner coma suddenly splits into multiple distinct peaks instead of one central concentration, that's when the entire story shifts. It goes from, hey, we caught an interesting new flash from this interstellar visitor to, oh no, we're actively watching an interstellar object come apart in real time. We're witnessing the breakup of something that traveled between the stars. Until that happens, if it happens, what we have right now is our first really clean, sharp glimpse of just how violent things can get inside this visitor from another star system. The forces at work inside this ancient ball of ice and rock, and who knows what else are powerful. The energy releases are sudden and dramatic. This isn't some gentle, predictable process we're watching. NASA just caught a brand new flash from 3IATLAS today. A real one, a powerful one, one that actually moved the comet. And if everything we've learned about this object over the past weeks tells us anything, if there's one thing we can be pretty confident about, it's that this won't be the last surprise this interstellar traveler has in store for us. We're along for the ride now, and honestly, I can't wait to see what happens.